Hey everyone, welcome to section 4 of Code in Place. This week we're going to be talking about images and functions, which is a really special section to me. Back when I was in CS 106 and I started learning about images and functions, it was really my first step away from the basic building blocks of programming, things like decomposition and control flow and variables. Now, don't get me wrong, those are really exciting, but because they're the building blocks of programming, they're kind of also like you're teaching the computer how to do things you already know how to do. Once we get to images, we start learning a little bit about how things like Photoshop, like Instagram, like movie making and special effects actually work, and the ability to see how the things you're learning in computer science right now apply to programs and output that you've seen in the real world countless times is incredibly exciting. Images are also a really good way to learn about functions. So far in Code in Place, we've told you a lot about decomposition and how crucial it is to writing programs that read understandably, but also are easy to develop and debug. But really, decomposition can only be as helpful as your functions can be. And this week, we introduced to you parameters and return values, ways of making you even more confident and more able to write functions that can do really, really complex things simply. So today we're going to be showing you how we can use functions to solve some really, really cool image problems. And without further ado, let's get into it.
All right, let's get started by doing a quick review of images and functions. So we're going to start with images, and in particular, we're going to start with a picture of my dog, Buddy. Now, my family moved to London from Singapore about a year and a half ago, and last winter, Buddy saw snow for the first time. You can see him here. He's kind of excited about the snow. He's kind of never seen something like this before, but very soon after this picture was taken, he decided it was both too cold and too wet for his taste, and so he went back inside. But that's not important right now. What is important is that images consist of pixels, which are just these tiny little boxes that a computer divides images up into. In this particular case, I've drawn, I believe, 6 pixels across the width of the image and 10 pixels down, but that's really not how pixels work. Pixels are far smaller than that. In fact, they're so small that usually an image consists of multiple hundred or thousands of pixels along each side of the image. So if you've ever heard an image's resolution as being described as 1920 pixels by 1080 pixels or something like that, that's telling you the dimensions of the image in terms of its pixels. So why am I telling you all of this? I'm telling you this because as we start thinking about how we want to interact with images in Python, we need to be thinking about them in terms of pixels. But before we even get there, we need to be able to access images in Python. And to do that, we make use of a library called the Simple Image library. Now, in lecture, we showed you that this library is a library that you import in your program, much like you might want to import the random library or the math library. The Simple Image library is just another library, this one written not by the people who wrote Python, but by someone else. And it allows us to interact with images in Python. In this particular case, imagine that I took this picture of Buddy on my phone, which I did, and I sent it to myself and a lot of friends, which again, I did. You can imagine that maybe the name I gave this file that I was sending everyone was buddy.png. So on my computer, I have a file called buddy.png. You may have seen images that are .jpg files or things like that. Those are just like PNGs. They're just different ways of storing image data that we don't need to worry about right now. So what we want to do is tell Python, hey, go find the image called buddy.png and store it as a variable because we'd like to use it a little later on. That's what variables are for. So that's what we're doing over here. We're creating what we call a simple image, and the information we give the simple image is the name of the image we'd like to represent. In this case, we want to work with buddy.png. So we create this simple image, and then we give that simple image the label img. Just like whenever we create a variable x, for example, and set it equal to 42, we're creating a label called x and labeling the value 42. So why is it helpful to now have this variable called img? It's helpful because it allows us to now interact with the image in our program. So for example, something we could do is get the height and width of the image. In this case, img.height gives us 10, which is the number of pixels tall that the image is. And width, which is equal to image.width, is the number of pixels wide that the image is. In this case, 6 pixels across. Okay, so that's kind of helpful, and we'll get to why in just a little bit. But before that, something else we might want to do is extract an individual pixel from an image. The way we can do that is by using another function, or more formally, a method that takes in the coordinates of a pixel that we'd like to take out. So in this particular case, I'm saying, hey, image, give me back the pixels at coordinates 2, 4. Now, keep in mind that whenever we're talking about pixel coordinates, we start with coordinates 0, we start counting from 0, and we start from the top left corner, meaning that this pixel over here in the top left is pixel 0, 0, meaning to get to pixel 2, 4, what we're going to need to do is start from here and count to 2, so 0, 1, 2, and then count to 4 going down. So 0, 1, 2, 3, 4. You'll notice this pixel is highlighted, meaning that it's the pixel we retrieve. And in this case, we're giving it the name pixel. That seems like a pretty descriptive variable name here. So now that we've got this pixel, what could we do with this? Why is it helpful to be able to have this pixel? Well, the first thing I want to point out again is that pixels are tiny. They're really, really small. Over here, you can kind of see that this pixel has a bunch of different colors. There's white, there's black for his lips, and like a little brown in that corner over there. But in real life, pixels are so small that they only contain one color, not even like gradients of a color. It's not just like blue and then light blue. It's just all one color in the image. So why is that important? Because it allows us to think about a pixel in terms of what that color is. So specifically, a pixel represents a single color, and that color is decomposed into 3 components, each of which is between the numbers 0 and 255. So a pixel has 3 numbers, each of which is between 0 and 255. The first of these numbers represents how red the color is. The second of these numbers represents how green the color is. And the third represents how blue the color is. Now, this is kind of a weird way to think about colors. I know when I think about my favorite color, I don't think, hey, this color is 128 blue, 42 green, and 37 red. That's not how I think about colors. I think about colors more generally. I just think of, hey, magenta or lavender or chrysanthemum or something like that. But computers can't do that. They have to represent numbers numerically, and this is how they do it. So if a color, for example, is very blue, what's probably going to be the case is that its blue number will be high, so like 200, and its red and green numbers will be slightly lower, and so on and so forth. So why is this helpful? It's helpful because now, if we know that we can think of a pixel in terms of its colors, and each of its colors is a numbers, we can now do math on an image to affect what color it is. And this is a really profound realization. It's really the basis of tools like Photoshop and Instagram, and in fact, a lot of movie special effects that you're probably used to seeing. But let me take it a step at a time. Let me show you how you can get and actually change these colors. So we can get a pixel, like I showed you in the previous line, by calling the getPixel function and passing in the coordinates we're interested in. In this case, I'm saying I want the pixel at coordinate 42, 100. The first thing we can do is ask the question, how red a particular pixel is. That's the way I do that is by creating a variable called red component and storing pixel.red in there. So what that's going to do is that's going to retrieve this number over here, and it's going to store it in this variable over here. Remember, at this point, once it's in this variable, it no longer has a sense that this variable has anything to do with redness. I've given it the name red component because I want to be clear what this number represents. But for all Python players, that number is just some integer between 0 and 255, meaning we can treat it just like we would treat any other integer. Another thing we can do is just set the pixels colors. So what we could say is something like pixel.green equals 42. What that's going to do is that's going to take the green component of the pixel and just set it to be whatever number it was over here. So if the green component was originally 100 and we set it now to 42, the pixel would become less green. And if the pixel's color was initially 0 for the green component and we set it to 42, the pixel would become more green. The last thing I want to say is that we can, like I said, do math on pixels. So we could say, for example, okay, take the red component of the pixel, that's this variable we created over here, divide it by 2, and set it equal to the blue component of the image. So why is that helpful? It's helpful because now we can say something like, okay, this pixel should be half as blue as it is red. Now, I know that's a really weird sentence. It's hard for us to mathematically reason about colors. Like, what's half of red or pink? That's not something you and I can think about. But it's, in fact, the only way computers can think about colors. And that makes it a really, really powerful tool for us to express to computers how we would like our pixels to be treated. Now, I'm going to show you in a few minutes exactly how that might look in a particular case. But before we get there, I want to show you how one other really important thing for images. And that's that over here, wherever I've called get pixel on this slide and this slide over here, I've just specified a particular coordinate. I've said, hey, I want the pixel at coordinate 2, 4, or I want the pixel at coordinate 42, 100. But that's not quite how we really want to work. Usually when we're doing something like Photoshop or doing something like Instagram, we want to change every single pixel in the image. So let me show you a way we can do exactly that. It turns out that there are two really common patterns that allow us to access each pixel in an image. The first of which is this line of code over here, for pixel in image. The second is this set of nested for loops over here, in which we first iterate over the range of possible y coordinates of this image. So starting at 0 and going up to the height of the image -1, because remember, we start counting from 0. And similarly, over here, we start at 0 and go up until the width of the image in pixels -1. Now, if this is a confusing block of code to you, and that's totally understandable, it's a tricky one, I strongly recommend checking out the lecture on images. We talk a lot about how we can use nested for loops to kind of access pairs of x, y coordinates. But the high level idea over here is that by the time we get inside the for loop, so in this particular case, just for pixel and image, and in this particular case, getting a pair of x, y coordinates, and then getting the pixel at these coordinates, these for loops go over the pixels in exactly the same order. So in both cases, the for loops are going to start in the top left corner and go row by row across the image. So we go over the pixels in the same order. The key difference is over here, in this second for loop over here, we have access to these y and x variables, which indicate to us where that pixel is in the image. Now, that's going to be really important if we want to do things to our image like move pixels around, because we need to know where the pixels are and from where they are, where they need to go. But if we're only interested in like changing every pixel in the image to a particular color or something like that, and don't care where those pixels are, then a loop like this is probably fine. So with that in mind, I want to now jump to a problem, which shows us maybe how we can start thinking about using some of these programs and some of these tools to write image programs of ourselves. So let's dive into it. All right, so let's rock and roll with our first problem of this week's section. It's a problem called image filter, and our goal here really is to design what we call the Narok filter. Now, what the Narok filter basically does is it takes images like this of Chris's dog Simba, and it converts them into kind of these more artistic looking versions of the image. It's a little hard to explain what's going on in the filter. I'll get there in just a second, but I do think at the very least, it looks interesting, which, you know, when you're talking about apps like Instagram is kind of what we're shooting for. So let me explain to you how exactly this filter works. What it essentially does is it tries to replace each bright pixel in an image with its grayscale equivalent. So that's a good working definition, but it's unfortunately not quite specific enough for us. We don't have a sense yet of what a bright pixel is, nor do we know what it means to make a grayscale version of a pixel. So what I actually want to do now is I want to draw some pixels out for you and work through with you how exactly I can figure out whether something is a bright pixel or a dark dull pixel. So what I'm going to do is I'm just going to draw 2 pixels out. I'm going to draw 1 pixel in, I don't know, maybe this pleasing bright shade of blue over here. And I'm going to draw another pixel in maybe a more dull, uninspiring shade of blue. You can probably tell my bias is coming through over there. I prefer brighter colors, but that's not important right now. What is important is we have these 2 pixels. Now, in an image, these pixels would be really, really tiny. They'd be like 1,000th the size of the side of an image or something like that. But I'm drawing them a little larger here because I want you to see what's going on. Now, off the top of my head, I just picked these two colors randomly, and I don't know what their red, green, and blue color components are, but I want to make this as realistic as possible for you. So it turns out Macs have a really cool app that allows you to see what a particular color is in terms of its red, green, and blue color components throughout. So as I drag my mouse around my program, you'll notice that these numbers over here are changing. I'll read them out to you in case they're a little small. But what I'm going to do now is just hover over this bright blue over here. And notice that it says that the color components of this color are red 148, green 242, and blue 245. Now, remember, these numbers are out of 255. So like in English, you could probably say that this image is, this pixel, excuse me, is very green and very blue, which makes sense. It's kind of like a bluish greenish color. And somehow there's some red in there as well. I don't see that red, but you know, the computer puts it there. So that's really helpful. Let's do the same thing now for this darker color over here. So what we're seeing now is that the red color on this image is, on this pixel is 23. The green is 0, and the blue is 155. I should say, by the way, Windows users also do have a way of doing this. I don't know what it is because I don't have a Windows computer, but I believe Microsoft Paint, at the very least, has a way for you to sort of copy colors from other places and see what their red, green, and blue components are. But that's not important right now. What is important is now we have data about these two pixels. We have data on this pixel, 148, 242, and 245, and data on this pixel, 23, 0, 155, meaning there isn't very much red in this color, there's no green in this color, and there's kind of some blue in this color. There's 155 out of 255 blue in this color. Again, we don't really have a sense of what that means, except to say that it looks like this color over here. Okay, so now that we know all of these things, the first thing we can do is define what we call the average color component of an image. And what the average color component of a pixel is basically the sum of these three numbers over here divided by 3. So what does that basically mean? Well, that means that what we want to do for this pixel, for example, is say, okay, add 148, 242, and 245. Oh gosh, I really should have done this before starting the section. 309, 635. So the sum of these three color components is 635. I really hope I got that math right. So that's what the sum of these three numbers over here is. But to find the average of those three numbers, what we then need to do is divide by 3. So we can put a little divide by 3 over there and a divide by 3 over there. And that is roughly equal to 211. So what I've done is I've divided by 3 and then rounded down, which gets me to 211. Pixels need to have integer brightnesses, so I'm just going to say 211 over here. It's generally okay. So now that we've got this 211, what we can say is that this is kind of the average color of this pixel. So what exactly does that mean? This means that we don't, this number alone, this 211, isn't enough to capture that it's a bright blue pixel, but it is enough to capture that it's kind of a bright pixel. There's a lot of color in this pixel. There's 211 out of a maximum of 255 color in this image, in this pixel, and so it's a pretty bright pixel. Let's go ahead and do the same thing for this image over here. Let's say for the second pixel over here. So the average color component of this pixel over here is equal to 23 plus 0 plus 155 divided by 3, which is equal to 178 divided by 3, which is 66. So 178 divided by 3, which is equal to 66. So once again, this 66 is the average color component of this pixel, meaning that out of a maximum 255 colorfulness, it's 66, meaning it's not a very bright pixel. Okay, great. So now in this problem over here, we've said that a bright pixel is an image defined as a pixel whose average color component is greater than 153. We just sort of arbitrarily chosen 153 because it's 60% of 255. So what does that mean? It means that, let's pull up my whiteboard again. It means that this pixel over here, and let's choose a fun color for this. This is a bright pixel because its average color component is 211, which is greater than 153. But this pixel over here is not bright because its average color component is only 66, which is less than 153. Okay, great. So that's all great. The last thing I want to show you is a grayscale pixel. Now, what a grayscale pixel basically is a pixel that has the same red, green, and blue color components. So let me actually prove to you that that's how the color gray works. I'm going to draw 3 blocks that are all grayish. I can't guarantee that they're perfectly gray, but here is one. Here's another. Let's actually include a white block and a black block as well. Here's a white block that might be a little difficult for you to see, but I promise it's there. And here is a black block. Okay, great. And what we're going to do is, once again, we're going to pull up this old color meter over here and take a look at the color components for each of these pixels. This one has a color component that is red is 200, green is 193, and blue is 191. So, you know, they're not exactly the same because this color isn't exactly gray, but they're pretty close to each other. This one over here is 83, 93, and 97. So again, those numbers are very, very close together. The color white is, in this case, 255, 254, 255. Again, this is slightly off-white. And I think that's just to do with how my iPad is showing up on my screen. And finally, black is, in this case, 102, but usually it's just 000. So the point over here is that to have a gray pixel, you basically need red, green, and blue color components that are about equal, or even better, exactly equal. So what does that mean? That means that in order to convert a pixel to its corresponding grayscale color, what we can do is first find its average color and then just set each of its color components to be that average color. So what that would look like is something like this. Let's go ahead and copy this bad boy and put it over here. And now what we're going to say is, okay, this gives us an average color component of 211. And so what we can do now is we can make a color that is 211. So let me go ahead and kind of show you what that would look like. So 211 is going to be a pretty bright gray. There's a lot of color in there. So this is kind of the brightest gray I have on short notice. And then its red would be 211. Its green would be 211, and its blue would be 211. Okay. So what does that mean? Well, what that means to me is that we now have a gray pixel whose red, green, and blue components are arranged in such a way that it also has an average color component of 211. If we added all of these together and divided by 3, we would get 211. But now it's a gray pixel instead of a blue pixel, meaning we have a pixel that is as colorful as this pixel over here, but also as bright, which is a really important distinction over here. Okay, so remember, when I say colorful, I'm not saying colorful in the way that you and I would use the word. I'm saying colorful in the sense that it literally contains as much red component, green component, and blue component summed together as this pixel does over here. Okay, great. So one thing you're probably seeing at this point is that one thing we're going to be doing a lot of in this problem is actually computing what the average color component of a particular pixel is. We need to do that to set and decide whether a pixel is bright or not. And equally, we need to do that to convert a colorful pixel to a gray pixel. Okay, so what I think is a really good idea when we're like, okay, here's a little bit of work that we're going to need to do a lot in this program is I'd like to think about whether or not we could make a function to do that work. So what I want to quickly do now is give you a brief conceptual overview of how I think about functions and how I think that would be helpful in this program over here. So what I'm going to do is I'm going to jump back to my slides, and you'll notice I've also got a section on functions. And let me quickly take you through kind of how I can think about functions as they're working. So when we're defining a function, what we're really doing is we're making two promises. The first promise we're making in the parentheses over here is what the inputs or the parameters to the function are. This is the information that the function needs to do its work. And so whenever you call functions, you'll need to provide two parameters, one that the function will call A and one that the function will call B. The other promise we make is what we're returning. So in this case, we did a bunch of like weird math in here. You don't need to worry about what that math is. And then we return this value over here. We're returning a number, meaning that whenever we call the function, we should expect to get back a number which we could store somewhere. So what does that mean? That means if we call this function, we now can pass in parameters. We can pass in 2 and 42. For these two parameters over here. And if I got my math right, that gives us back 29. And separately, if we call my function with two separate parameters, that is 10 or 15, we get back 85. So at this point, there's a really important conceptual thing I want to make clear. And that is that at a high level, functions are kind of like this. They're a box which take in parameters and spit back return values. But what's most important is that when we're writing a function, we don't care about where the parameters are actually coming from. Like over here, I said just randomly that the numbers I wanted were 2 and 42 or 10 and 15. But by the time we got to this function over here, we didn't know that. The 2 and the 42 may have come from variables. They may have come because the user typed in those numbers or things like that. The function just doesn't care about those at all. Equally, the function doesn't care what's going to happen to the return value once the function is done. All it cares about is giving you back that number, the same way that like if your manager asked you to do a piece of work, you'd give it to them and then presumably they would decide what to do with it. You would no longer have a say in that discussion. So that's kind of the idea of a function. A function is something that does work for you, but doesn't care why it's doing that work or what's going to happen with that work. Really, the only job of a function is to take the parameters we're given and produce the return value we promised. So going back to our code over here, what I really think we need is kind of a function, which we can draw out over here. Let's choose a fun color, that one over there. So here's our function. I'm just going to say function. And what I want is a function that if we look at the sorts of calculations I was doing over here, I want a function that takes in a pixel and gives me back this number over here. So what I want is a function that takes in a pixel and gives me back an average color component. So let's go ahead and write that function. So we're going to jump to our code over here. And what I'm going to say is up here, def, and I think a good name for this function is like get pixel average. And going back to this diagram over here, the input that this function is going to accept is a pixel. That's like what it takes in. So what I'm going to say, okay, give me a pixel. And now what we need to do is figure out the average color component over there. So looking back over here, the way we did that is, like I said, when I was going through my math, I first computed the sum over here, and then I divided it by 3 and returned it. So let me go ahead and write those out for you. We can first say that the color component sum is equal to pixel.red plus pixel.green plus pixel.blue. I forgot the name of the color for a second. Okay, and once we have that component sum, which is just this top part of the fraction over here, 635 or 178, what we then need to do is divide by 3. So we can say something like average color component is equal to color component sum. What I'm actually going to do here is do an integer division. The reason I'm doing an integer division is because I want to get kind of a whole number over here. The simple image library does understand floats, but really just for our own sakes, we know that pixels should always have integer color values. They should always have like 5 or 6 or 100 or 101, never 100.5. So that does that. And now the last thing we want to do is we want to return this average color component over here. And the reason that's important is because now what we're fulfilling the second arrow in our function diagram. So if we go down here, this is what we're returning, the average color component. So again, to clarify, the pixel in the parentheses over here is the arrow going into the function, and the return statement is the arrow coming out of the function. I think it's a really good idea whenever you're writing programs like this is to actually draw diagrams like this. It really helps you clarify what exactly your functions are expecting to accept and return. Okay, so now that we have that sort of hefty piece of the work out of the way, I think what is a really good idea now is actually to start writing the rest of our program. So we could write a function that applies the Narok filter to this, but here's the fun part. This is Chris's dog, Simba. I also have a dog called Simba. So let me go ahead and show him to you real quick. This is Brum's Simba. So this is Simba also seeing snow for the first time. You notice he's also looking kind of inquisitively around him. He liked it a lot more than Buddy did. So he stuck around for a little bit and sort of ran around and rolled in the snow and did all that fun stuff. And so this is the picture that we're going to be applying the filter to. As a fun fact, I haven't actually tested the code on this picture before. So you and I will be seeing the Narok filter on my Simba for the first time together. But that's that. So let me go ahead and quickly show you what the program is doing right now. The main function is just loading in that image by saying simple image images/simba.jpg and then showing it. Meaning that if I run my program, Python3 section filter.py, we just see this picture of Simba pop up. It hasn't been edited or anything like that, but that's okay because I like looking at my pictures of Simba. But what I do want to think about now is how exactly we write this function. So we know that what we want to do is look at every single pixel in the image, and we want to, for each pixel, basically say, okay, if this is a bright pixel, replace it with its grayscale equivalent. Otherwise, leave it be. So let's go back to our slides and look at what the two ways of actually going through our pixels were. There's this single dimensional for loop over here, the for pixel in image loop, and then there's the double loop over here, the for y in range image.height, for x in range image.width, pixel equals image.getPixel. And if you remember, the only real difference between these two loops is whether or not we need the coordinates of the pixel. Now, I'd argue that for this particular case over here, we don't really need the coordinates of the pixel, right? We just need to look at an individual pixel and decide whether or not it's bright and maybe change it to gray if it is. What that means is that we probably don't need a separate loop to give us the coordinates of a pixel because we're not going to be moving it around or anything like that. So if we go down and look at our code over here, what we can say is, okay, because we probably need a single dimensional thing, let's go ahead and do something like this. For pixel in image using that first for loop over here. And now that we have a particular pixel, what we can say is, okay, let's get the average component of that pixel. So we can go ahead and do that by saying pixel average is equal to whatever I call that function, get pixel average. and we're going to pass the pixel in as a parameter. So what this is doing is it's now using this box over here. So we're taking whatever gets returned over here, and what's going to happen with that is we're going to store it in a box called pixel average. So that's what's going on over there. But now that we have this pixel average in a box, this average color component of a particular pixel, what we can do is say something like if pixel average is bright, and I'm just writing in English right now, I'm not writing in Python. What we can then say is, okay, set the pixel to be grayscale. I always get confused as to whether Americans spell gray with an A or an E. I think that's how Americans do it, but don't be offended either way. Okay, so now what we know is if the pixel is bright, we want to replace it with its grayscale equivalent. And like we saw up here, the way we convert a pixel to its grayscale equivalent is by setting each of its components equal to its average color component. Meaning we could say something like pixel.red is equal to pixel average, pixel.green is equal to pixel average, and pixel.red is equal to pixel average. Okay, great. So now the last thing to do is this bit over here, checking that the pixel average is bright. And we said up here that, hey, the way we check whether something is bright is just checking that its average component is greater than 153. So let's go ahead and store 153 in a constant because it's an important number and we probably should clarify what its for purpose is. So let's say something like bright threshold. Did I spell threshold right? I did not. We only have one H in there. Is equal to 153. And now what we can see over here is, okay, if the pixel average is greater than 153, run this code. Except instead of saying 153 over here, I already forgot to use it. We're going to use this constant, bright threshold. Okay, great. So now take a second to reflect on what's going on over here. Think about exactly how this function specifically is being used to help us compute the pixel average, and then how we're actually modifying the pixels in place. Once you've done that, go ahead and rejoin us. What I'm going to do now is run this program. And I'm actually kind of a little nervous to see how Simba looks with the Narok filter, but let's go ahead and do it. Okay, it's taking a while. Okay, interesting. Well, it doesn't look maybe as different as Chris's Simba did with this, but I don't know, that's interesting. I've never seen him look like that before. Just for fun and giggles, let's also try the picture of Chris's Simba, which is just Simba SQ, and see what happens over there. And great, yeah, that seems to look kind of like what it looks like over here, which is pretty exciting. We are getting the correct colors out. So that's awesome. I think the other thing over here is when you run this program, you kind of see it taking a second or so, especially on the picture with, especially in the program with normal Simba. And I think that's kind of cool because it kind of makes you feel like the computer is doing work, like it's taking the computer a while to like do all this math and affect the picture. And I just think that's kind of a cool feeling to have. So this is a really important program. It's important because it's our first example of using a function with parameters and return values in section. And that's a really, really kind of big threshold or milestone to have made. But equally, it's important because I think we're just doing something kind of cool over here. We're writing a program that is mathematically looking at images and manipulating them in some way. If you find this interesting, definitely go ahead and check out the images lecture, which hopefully you've done by now already. We talk about a lot of cool ideas as to how this mathematical treatment of images can be used to achieve some really cool effects like green screening in a lot of movies you've seen. So with that, we're actually going to move on to one other problem now. This is kind of an extension problem. It's just to make sure that you can kind of understand a little bit more about how you can mathematically consider images. So let's do it. So this is our second problem of today's section, and it's a problem called trim crop. Essentially, what we want to do is write a function that takes in an image as a parameter, as well as a number called trim size. Our goal in this function is to basically return a new image with that many pixels trimmed off each end of the image. So if you take a look over here, what we did is we called trim crop on this picture of Carol over here, and we then removed 30 pixels from each side of the image over here. So why exactly is a program like this useful? Well, it's useful because a lot of the time in photo editing, you do need to crop images to get rid of stuff on the outside if you want to focus on just one part of the image. But sort of more educationally, I think this is also a really, really helpful problem because it helps you start kind of mathematically considering pixel coordinates. So I've talked a little bit in previous problems about how we didn't need to care so much about pixel coordinates, and so we could just use the single for loop, not the nested one. But in our problem like this, where we're probably going to need to care about where pixels are and move them around possibly, it becomes a lot more important to need to use a nested for loop. So with that in mind, because firstly, this is an extra problem for the section, and secondly, because it is really important to understand, I'm not actually going to give you the entire solution over here. What I'm going to do is instead tell you a few of the important things that I would think about as I was solving a problem like this, and maybe get you started on how to do something like this. But I'd strongly recommend in your own time, you go through and solve a problem like this, especially if you're considering doing something with images for your final project. We've seen a lot of those in the past, and it becomes really helpful to be able to know where a pixel is and how it can be moved somewhere else in an image or to an entirely new image, as the case may be. So that's kind of what we're going to focus on in this. So what I want to do is, this is a picture of Carol, which is great, but what I want to do is actually try thinking about trimming images on another picture. So this is a picture of me, Simba, and Buddy. My hair is very messy in this photo, and it's making me self-conscious, but that's okay. The goal over here basically is that we want to sort of look at this picture and say, hey, you know what? There's a bunch of like empty space in this picture, like all the stuff above my head, all the stuff below Buddy, and everything kind of to the right of me. And so what I maybe want to do is just like get rid of some of the border of this image over here and just make it a little tighter. So I might call that trim image function that I just showed you, and it might give me back a slightly smaller version of the image like this. So what I'm going to do is just actually put these two side by side so you can see a more direct comparison. So let's go ahead and move that over here. All right, great. So you'll notice that what I've really done over here is I've removed some number of pixels from every part of the image. So you'll notice that part of Simba's tail has been cropped off, but also all of the stuff above my head is gone, and a lot of the stuff below Buddy's feet is gone. And also you'll notice that like this right bit of the shadow over here isn't in this image because it's been cropped out. So what I want to do is talk a little bit about how exactly we can solve a particular problem like this, because it's not easy. So what I want to do is just start by thinking about some of the things that changed between these two images, because really what we want to figure out is how, let me move these slightly further apart, how we can go from the image on the left to the image on the right. And really immediately just in that sentence there is the fact that these are different images. And what most gives them away is that they have different sizes. So whenever you have two images of different sizes, what you usually want is two simple images. One that like represents the image as it currently is, and one representing the output image. So once we have this, what it really becomes a question of is figuring out how to populate images like this. So what I mean by that is by default, what I would probably do is something like this. I would make an empty image, which is the size I need it to be, and we'll talk about that size in just a second. And then what I would want to do is basically go through this empty image pixel by pixel and figure out what pixel needs to go here. So for example, this top left pixel is probably going to be like the pixel over here or somewhere around there, like the bottom bit of this tree. And so what I'd probably want to do is zoom in over here and copy like that brown pixel to the very top left of the screen. I would then look at the very next pixel and say, okay, you know what? That's probably going to come from right next to it in the tree. And so we're going to put another pixel over there, and then so on and so forth. We just keep doing pixels. And then a little later on, when we got to the grass, we'd start drawing green for the grass, and then like some black for my hair over here. And there would probably be some yellow for Simba over here, and some brown for Buddy. So obviously this isn't the entire image. This is just like a very small part of the image, but that's kind of how we approach problems like this. We start with a blank image and then fill it up. So let's start a little bit more about what this blank image is going to look like. Let's assume that this image is, let me choose a color here. Let's say 500 pixels wide, and let's say 300 pixels. It isn't, it's a little more than that, but let's assume it is. And let's assume what we're doing is we're trimming it down by 50 pixels on each side. So what that means is if I draw like the little border that actually is being trimmed, and I'm going to do that in red over here. I'm going to be a little approximate over here, but really this is kind of the bit of the image that we're keeping. The bit in red is kind of the part of the image we're keeping. So what we're really saying is that we want this distance to be 50 pixels. We want this distance to be 50 pixels. We want this distance to be 50 pixels. And we want this distance to be 50 pixels. Okay, great. So that's kind of what we want happening over here. We want to crop off 50 pixels from every single side of the image. So what that means then is what we can now do is calculate what the dimensions of the output image are going to be over here. So for example, if we think about how tall this output image is going to be, we know that it's going to be the total height, 300 pixels, but then we're going to subtract these 50 pixels. We're going to subtract these 50 pixels, meaning that the cropped image is actually 200 pixels tall. And equally, the width of this image over here is going to be the width of this total image minus this border over here and minus this border over here, meaning that it's going to be not 300, but 400 pixels across. Okay, so that's super helpful. Now, what we probably want to do is say, okay, we know that the output image is going to be 200 by 400 pixels in this particular case, but how do I actually make an image of that size? So as it turns out, there actually is another simple image function that's super helpful that lets you make these blank images. And the way that function works is a little something like this. We could say output is equal to simple image dot blank. And then we would pass in the dimensions of this image over here. The order in which those dimensions get passed in is the width and then the height. So we'd say 400 followed by 200. What that would then give us is this blank image over here. It's totally white to begin with. There's nothing in it. And so what we'd want to do is actually start copying those pixels over. So let's talk a little bit about exactly how copying those pixels is going to look. What I'm going to do is take this picture. Whoops, that's not what I want to do. What I want to do is take this image over here, which refuses to be copied, which is unfortunate, but that's all right. So what we want to do is we want to take this image over here and we want to figure out how to move pixels from this image over here to this image over here. So let's talk a little bit about how exactly that's going to work. And let's use maybe a slightly simpler version of the image for this. Let's go here and say, okay, here's my uncropped image. And all this uncropped image contains is like a blue circle in the middle. And let's say a pink rectangle in this corner and a pink rectangle in this corner over here. Okay, great. Let's also say that this image over here has a width of, let me choose a color, I don't know, 200 pixels. And its height is 150 pixels, meaning that if we now want to create a cropped version, and let's say we crop off 25 pixels from each side, what we're going to have is a smaller image over here that has like a smaller pink rectangle over here, a smaller pink rectangle over here, and then a blue square, a blue circle in the middle over here. So to be clear, what's really happening is we have this outer version of the image over here that has been cropped away. And what that outer image would look like is the rest of the rectangle would be in this outer image over here and shaded in. But we've cropped those parts of the rectangle out. And so we want to get rid of them. So I'm going to erase all of that. So we're just left with the cropped version of the image. So really what we want to do now is say, okay, the way we're going to be creating this image is going pixel by pixel over here and identifying which pixel we want to copy over from this image over here. So let me talk a little bit about how exactly that math would look. Again, let's quickly clarify what the dimensions of this image are in case they're helpful. So we know that if we're cropping 25 pixels off each side, either dimension of the image will be reduced by 50 pixels, meaning this becomes 150 pixels and this becomes 100 pixels. All right, great. So now that we've done that, let's talk about some arbitrary pixel over here. Let's talk about, for example, this pixel at the very top of the circle. We know that that pixel and this pixel have to be the same. So we can draw an arrow to kind of map that out for us. And so what I really want to do is figure out what the coordinates of the pixel are in this image over here and in this image over here. Once we have that, I'll show you how why that could be helpful. So let's go ahead and assume that this pixel on the right is at coordinates x, comma, y. All right. So what that means is that this distance over here is y pixels, and this distance over here is x pixels. All right, so that's just what a coordinate means. So given that, now what I'd like to be able to do is see whether we can figure out, I'm going to choose a different color, what this distance is. Let's call it old y, and put a little question mark, and this distance, old x. Because here's the deal. If we can figure out old x and old y given a value of x and y, then we can find kind of the source pixel for this particular one over here and copy it over. And I'll talk about how exactly copying a pixel looks. So let's think a little bit about how exactly that works. Well, kind of the idea over here is, remember, we have, I'm going to draw this one last time. Here's our cropped image, which has a little pink rectangle up top here, a little pink rectangle up top here, and then a blue circle in the middle. And then remember, we also have this sort of larger image that we're cropping away over here. So what we know is that, for example, this distance over here is x. Sorry, this distance is y, and this distance is x. So what we need to do now is figure out what that distance and that distance are. Like, those are the same as old y, and old x over here. So one insight we immediately have is that we're trimming away parts of this image. So we actually kind of know what this distance and this distance are, right? We know that for this particular case, wherein we trimmed by 25 pixels on either border, we know that in another color, this distance is 25 pixels, and this distance is 25 pixels. So what does that mean? Well, it really means that this distance over here, this green line, is equal to the purple line plus the orange line. That's y plus 25. And equally, this green line over here is equal to this purple line plus this orange line. So x plus 25 pixels. So let's go ahead and note that down for ourselves. Let's say that old y is equal to y plus 25, and old x is equal to x plus 25. Okay, so why is that helpful? It's helpful because now we could say something like this. We could say, let's get another color. For y in range image dot height, and then for x in range image dot, that's not how you spell width. What we now know inside this loop over here is that x, y are coordinates in the image. So this is a loop you've seen a lot of times in the past. This is just the nested for loop that we also had in our slides. But here's the thing. What if instead of image, which is the image we're cropping, instead of that, we used new image? So what if we said something like new image dot height, and equally new image dot width. So that's helpful because now we know that x and y are coordinates in the new image. Meaning what we're really doing is going over all of the possible coordinates in this image over here, or more specifically, this blank image over here, and we're getting each pair of coordinates back. What we also know is that if we have an x and a y, we can calculate the old x and the old y, which are the x and y in this image over here. In fact, I think a better name for them might be source x and source y, because they're the source of our pixel. So what we can then say is, okay, where did my color go? Source x is equal to x plus 25, and source y is equal to y plus 25. So why is that important? That's important because now if we have two images, say our big image over here, as well as our cropped image over here, we could take any coordinate in this image over here, let's say x, y, and we would know that the matching coordinate, which would be somewhere around here in the original image, would be source x, comma, source y. Okay, that now means that we could, given that we have both of these pixels and their coordinates, we can now copy this pixel into that coordinate over there. So the last question we therefore need to ask ourselves is how we actually copy pixels. So let's think about that. Let's imagine that we have one pixel, this pleasing bright blue pixel over here. and another pixel, which is just a blank white pixel. And what we'd like to do is copy this pixel over here to here. So what we would then need to say is, okay, let's think about what color this pixel actually is. Let's get our red, green, and blue values for it. So the red value of this pixel is 42. The green value of this pixel is 169, and the blue value is 245. And so in order to make this pixel this color, what we would need to do is also set its red, green, and blue values. So we would copy these three to here. So that really is all of the moving pieces of this problem. There's a lot of them, so I want to take some time to quickly go over exactly how we can compute each of those pieces again. We started with finding the dimensions of our image over here. So the way we did that is by saying the dimensions of the new image are the dimensions of the old image minus the parts that we trimmed off. So let's actually make a note to ourselves over here. Let's say 1 dimensions of new image equals dimensions of old image minus trimmed off borders. Great. The second thing we realized is this sort of stuff over here, where basically we said, if we have a coordinate in our new image, we can figure out which coordinate in our old image that pixel is coming from. Remember, at a high level, what we want to do is copy the correct pixels from this image over here to this image over here. So let's go ahead and write that down. We want to copy pixels from original image to new image. And we also know that source X is equal to X plus whatever is being trimmed away. So up here it was 25, but remember there's actually a variable which stores that information. So we'd say something like source X equals X plus 25 and source Y equals Y plus 25, except instead of 25 in both these cases, what we'd actually say is trim size and trim size. And the last big takeaway over here is that copying pixels is the same as copying color components. So that's kind of what we did up here. We said, if we want to make this pixel the same color as this pixel, what we're going to do is take its red, green, blue color components and stick them in this pixel over here. So those are kind of the three big ideas for a problem like this. Firstly, that we can calculate the dimensions of the new image based on the dimensions of the old image. Secondly, we can calculate the coordinates in the old image from coordinates in the new image. And finally, that to copy pixel is to copy color components. Now, I went over that pretty quickly because I just wanted to identify for you what the big three parts of this problem are. I haven't actually solved the problem, and I'd encourage you to take some time to think about how you might do this. It might be really helpful for you to check out the green screen example from lecture that uses very similar logic to this problem over here and might be a really good way to start. But with all that said, keep in mind that all of this is just really getting to the fact that when we're dealing with images in Python, what we're really doing is just math. Whether that math is to change the color of a pixel or to change the position of a pixel or copy a pixel from one image to the other, really what it always boils down to is figuring out how to reduce the problem to numbers. In this particular case, we reduce the problem to numbers by boiling it down to a question of coordinates and dimensions. And in the previous problem, we boiled it down by reducing the color of a pixel to its color component number. So that's really the big takeaway from today's section. And definitely take some time, if it's still a little tricky for you, to look at these problems, both the trim crop problem as well as the add border problem. They're both really good ways of practicing this kind of reduction of an image to numbers. But with that, that's the end of our section this week, and have a wonderful weekend.